Yes, sir.
Hello, good evening to all of you.
Good evening, sir. Good evening, sir.
Good evening, sir.
Good evening. Am I audible?
Good evening.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Is my screen visible to you?
Yes, sir. Visible, sir.
Fine. Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Ananda Kumar,
Yes, sir.
Arnachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Yes, sir.
Jagan,
Yes, sir.
Kesav Prasad, Kesav Prasad, Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Sir, both Keshav Prasad and Prabhakaran are there on the call, sir. It seems something mic is not working.
Hi, sir.
properly,
Sir.
Mic, okay, mic is not working for both of them.
Sir, am
Yes,
I audible,
correct.
sir? I am trying
Yeah,
to.
noise coming in, sir.
Yeah, you are audible.
Yes, sir. Sir, mic was not initially working, sir. Sorry, sir.
Kesav Prasad and then Prabhakaran. Okay, Prem Vinayak,
Present, sir.
Rahul,
Yes, sir. Yeah.
Raujan Kumar,
Present, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Malish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijay
Present, sir.
Vikas,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj.
Present, sir.
Okay, so all of you are present today.
Sir, Prabhakaran, sir, sorry, my mic didn't work. Sorry for.
Okay, I have entered.
Yes, thank you, sir. Thanks.
Okay. Could you please mute your mic? All of you, could you please mute your mic? Okay. So, welcome back to this class on IC engine combustion and pollution. We are in chapter 2. Now we are in the last topic of this chapter 2. We are now discussing about the chemical kinetics. As we discussed in the last class, thermodynamics provides steady state information about the combustion system, but that is not enough. Combustion is not about only steady state information. We need to know time-based or transient information that is provided by chemical kinetics. So apart from the steady state information, useful information we derive from thermodynamic concepts, we also need to know time-based information. Then only the combustion analysis will be complete. So what kind of transient information you can get from chemical kinetics? As I said, you can know about the rate of consumption of fuel and air, which are reactants in the combustion system, IC engine combustion system. So I need to know how much time is required for consumption of fuel and air. That is one important information. Second one, I need to know the rate of formation of product, because some of the products are pollutants from IC engine. That is where the objection for IC engine comes into picture. And today we talk a lot about electric vehicle, because we don't want any tailpipe emission from the engine. And this tailpipe emission is primarily due to the combustion E1. So combustion E1 produces several products. Some of them are pollutant. I need to control this pollutant because it's a legal mandate, right? As you know, it's mandatory to reduce the concentration of this pollutant below certain level. I need to track when the pollutants are formed in the engine cycle time. That will help me to come up with a suitable pollutant control strategy. To come up with a suitable pollutant control strategy, I need to know when the pollutants are formed in the engine cycle time. So I would say that this is one of the important information, transient information you need to know, that is provided by the chemical kinetics. The last and the most important one is the rate of heat release. The rate at which the thermal energy release is again an important information, because I need to time this heat release appropriately. Any untimely heat release is of no use in IC engine context. You know, in the engine cycle, right, in an engine operating cycle, there are well-defined processes, and we need to ensure that this thermal energy is released during the expansion stroke, start of expansion stroke, so that you can convert that thermal energy into work in this energy conversion device, which is IC engine. Okay, so I need to time thermal energy release appropriately. Then only I can maximize the power output or torque output of the engine. Okay, so this is again an important information, rate of heat release or thermal energy release, and that will ensure that we allow this thermal energy release to happen at appropriate time. You know that thermal energy release during a suction stroke or a compression stroke is of no use. We cannot convert them into work. It has to be released during the expansion or power stroke. So I need to know the time-based information. These are the useful time-based information that chemical kinetics provide. Chemical kinetics is all about, it's a branch of science that deals with finding out the rate at which a chemical reaction proceeds. So here I have also discussed one of the important feature of the combustion event. The rate of progress of a reaction is highly sensitive to temperature. When the temperature is increased, the rate of progress of the reaction also increases. So one of the distinct feature of this combustion process is the thermal energy release. Since it's an exothermic reaction, there is a energy release. Because of energy release, there is a rise in temperature. This rise in temperature provides a positive feedback to sustain the combustion event. The rate of progress of a reaction depends on the temperature. Okay, it's highly sensitive to temperature. Higher the temperature, higher will be the rate of progress of reaction. Now, since combustion is an exothermic reaction, there is a energy release, there is a rise in temperature that in turn increases the rate of reaction. This is one of the important feature of this process, which you cannot find in any other process, right? So you have to only initiate the event, combustion event. Once the event gets initiated, it will go on its own. That's why I say that it's a self-sustaining process. Self-sustaining process, it will go on its own. Okay, as long as sufficient radicals are available, the combustion event will continue to happen on its own. You have to first initiate the combustion event. The way you initiate combustion event is different in SI and CI engine. In SI engine, you discharge electric spark. In CI engine, you provide high pressure, high temperature air at the time of fuel injection. That provides the initial thermal energy to initiate the combustion. So I will continue my discussion about the chemical kinetics, and after this is over, whatever concepts we have discussed here in this chapter 2 will be discussed in the form of problem. I have today sent you an email with a list of problems. There are 5 problems I have sent to you along with the table that we will be using it to solve the problem. So whatever concepts we have studied here, based on this, we will solve 5 problems, and I would like you to submit those 5 problems as an assignment. So the way it will go is I will discuss about the solution procedure for those 5 problems. Note down the solution procedure, solve the problem by yourself, then submit it as an assignment. You can send it over my email. Okay, so you can take 1 week time, and by next week you can submit it to me. Next week by Wednesday, you can send it to my email ID. Okay, today after this topic is over, I will discuss the solution procedure. So as I said, in kinetics, we are interested to find the rate of progress of a reaction. Before we discuss about the rate of progress of a reaction, we have seen that there are 2 types of chemical reactions. One is a global reaction, which is a single step reaction. The other one is elementary reaction. I have explained about what is a global reaction and elementary reaction based on H2O2 reacting system. This is the simplest reacting what a global reaction is and what an elementary reaction is. Okay, so as we discussed, the chemical reaction will proceed only through elementary reaction steps. Stable molecules cannot react among themselves, which we consider in the global reaction, whereas in an elementary reaction, you will have sub-reaction steps through which radicals are formed, and radical formation initiate the combustion event, and as long as sufficient radicals are available, the combustion event will sustain. So based on our understanding about global and elementary reactions, we discuss about how to calculate the rate of this elementary reaction by using this equation. This equation is also called law of mass action. Q dot R, rate of progress, is proportional to concentration of A raised to the power small a, concentration of B raised to the power small b, where A and B are the reactants. Okay, so what this equation tells you is the rate of progress of a reaction is directly proportional to the concentration of the reactants, in this case, fuel and air are the reactants in IC engine system. To remove this proportionality symbol, we introduce a constant K, and that is called Arrhenius rate constant or Arrhenius rate equation. So this K is expressed in terms of two important parameters, A0 and EA. What a chemical reaction is from a molecular perspective or a microscopic perspective is the chemical reaction happens due to collision of the molecule. So once the molecule collide, molecules collide, it will form radical by breaking chemical bond. The term A0 captures the frequency at which the molecules collide with each other. Okay, and the term EA, activation energy, captures the effect of energy, chemical energy that is required to break the bond. Okay, during molecular collision, the radicals may form, may not form. When do the radicals form? The radicals will form once the molecules, colliding molecules, have sufficient energy to break and form radical. Okay, so you can consider that as a successful collision. When the radicals are formed during collision, it is a successful collision. So the collision event may be successful, may not be successful. That depends on how much of activation energy is available. So this term is capturing the energy that is available to form radical activation energy, and the term A0 captures how frequently the molecules are colliding with each other. Okay, so these two are important terms, and these are captured by using this term K. Actually, A0, EA, small a, and A0, EA are obtained from experiments. So we use equipments like shock tubes, which are used to find the rate of progress of a chemical reaction, Q dot R. From that, you will be able to get A0 and EA for important chemical reaction. Okay, that is how people calculate the rate of progress of this elementary reaction. Moving ahead, we need to know about how we can calculate the rate of a global reaction, global single step reaction. The problem with elementary reaction is, for a hydrogen oxygen system, the elementary reaction for hydrogen oxygen system include 21 reactions. For isooctane C8H18, you have around 3606 reactions, elementary reactions. So isooctane is one of the hydrocarbon present in gasoline and diesel. In fact, it is present in gasoline to a larger amount. We already discussed about this in chapter 1. One of the hydrocarbon include these many number of elementary reactions. Now you can imagine the number of elementary reactions that is undergone by gasoline and diesel, which is a complex mixture of hydrocarbon. This is only one hydrocarbon present in gasoline and diesel. Likewise, you have many such hydrocarbon. What is the typical number of hydrocarbon we discuss in chapter 1 for gasoline and diesel?
100 to 1000.
Yeah, 100 to 1000. So you have anywhere between 100 to 1000 different hydrocarbon. You can imagine the number of chemical reaction steps or elementary reaction steps gasoline and diesel will undergo. Now you can understand the complexity of the combustion system, IC engine combustion system with gasoline and diesel as fuel, because these fuels as such are very complex, and each of the hydrocarbon present in this fuel will undergo these many number of reactions. Then how do we go about it? How do we handle this? So we also do a lot of CFD analysis. Okay, when you do computational fluid dynamic analysis of engine combustion, you need to have a model for the fuel, right? Otherwise, you cannot predict the thermal energy release. Fuel plays an important role. Okay, so you need to have appropriate model. How do we go about it? How can we handle such a complex fuel with n number of elementary reaction? Any code, CFD code cannot handle such a large volume of chemical reactions, elementary reaction. The code is going to crash. So considering this complexity, there are two approaches that are followed to carry out combustion simulation of IC engine process. One of the approach involve, I already said about it, surrogate modeling approach. So what is the surrogate modeling approach? We discussed this in chapter 1.
So basically, sir, as you had taught us that any hydrocarbon can be classified in five groups, and basically while doing the CFD simulations, one of the hydrocarbon property is applied, and it is assumed that that will be happening throughout the system. Like what I mean to say, that is applied to different type of hydrocarbon, and then this what I mean to say is calculation is done further.
Perfect. So surrogate model means we are going to choose few representative hydrocarbon for this 1000 different hydrocarbon. I'm going to choose only few hydrocarbon, and this few hydrocarbon should mimic the characteristic or capture the characteristic of this 1000 hydrocarbon. It means I need to pay attention to these few hydrocarbon because this few has to capture the characteristic of 1000. Okay, that is where the challenge is. So fortunately, as we discussed in chapter 1, all these 1000 hydrocarbon can be binned or grouped into 5 classes. Okay, all this will collapse into only 5 classes. So what you will do, you choose 1 or 2 hydrocarbon for each class, so that you have a representative for each of the hydrocarbon class present in gasoline and diesel. That is how you capture the overall characteristic or mimic the overall characteristic of the real fuel, which is much more complex. Any code cannot handle. Okay, so you choose few hydrocarbon based on the class information, hydrocarbon class information. Okay, and then use the reaction step, elementary reaction steps of few hydrocarbon to capture this different 1000 different hydrocarbon. Okay, here again we cannot go ahead with see here only in one hydrocarbon you have 3606. Again, you cannot handle such a large number of reactions. What they will generally do is they will adopt something called skeletal mechanism, skeletal reaction mechanism. The skeletal reaction mechanism is obtained from detailed mechanism. Say for example, if you take isooctane, this has around 3606 detailed elementary reaction. What they will do here is they will reduce this 3606 to say around 100 to 200 reactions, chemical reactions. How do they do? There is a technique involved. They will retain only the primary features of these 3606 reactions, and they will ensure that the major species produced by this skeletal mechanism and detailed mechanism are similar. Okay, so they will ensure that there is no thermal energy release variation and there is no change in the major species. They will remove all the minor species from the detailed mechanism so as to arrive at this skeletal mechanism. Okay, this is one of the approach. Follow surrogate modeling approach, choose few hydrocarbon with skeletal mechanism, carry out combustion simulation of real fuel. This is one of the approach. The second simplest approach is indicated here, which is called global single step reaction. So here you are going to use only. Hello?
Sir?
Yes.
Sir, this surrogate model approach, how do we select this hydrocarbon, sir? Like, for example, if you go for diesel, based on how much the N-paraffin contribution is there in the diesel, based on that we will take, or how it will be?
Yes. So yes, exactly. So based on N-paraffin, isoparaffin, cycloparaffin, aromatics. So okay, these are the 5 classes, right? So what you will get when you analyze the composition of diesel, you will get information about how much of each of these class is present. You will. That is what I have discussed in chapter 1, right? Composition of diesel and gasoline in terms of hydrocarbon class. So you know how much of particular hydrocarbon class is present in gasoline or diesel. With that information, you choose 1 or 2 hydrocarbon for each class.
Okay, sir.
That is how you arrive at these few hydrocarbons. Okay.
Yeah. Thank you, sir.
And then you choose elementary reaction based on skeletal, not detail. Skeletal mechanism for this few hydrocarbon and carry out the combustion simulation. This is one of the approach. The second approach is a much simplified approach. Here what we are going to see is a global single step reaction mechanism. So in this case, you are going to simulate all the complexity of this multi-component fuel undergoing n number of reaction steps only with only one step, reaction step. That's why it is called single step or one step reaction. Global reaction. Global is called overall reaction. Okay, like you have represented this H2 and O2 for a hydrogen oxygen system. If you recollect, this is a global reaction for hydrogen oxygen system. H2 plus half O2 forms one H2O, 1 mole of H2O. This is global single step reaction mechanism for H2O2 system. Now for our hydrocarbon fuel, gasoline and diesel, this is a single step, only one step chemical reaction, and this is much simplified. Although it is inaccurate, it provides you with a quick outcome, okay, because it's only one step. Okay, so let us see how we can go ahead with this one step and find the chemical reaction rate. So this is a general hydrocarbon single step reaction under stoichiometric condition. Phi is 1, okay, phi is 1 stoichiometric condition. C alpha H beta is any hydrocarbon fuel with alpha number of carbon atom, beta number of hydrogen atom. Alpha plus beta by 4 is a stoichiometric coefficient. O2 plus 3.76 into is air. So fuel and air combust and produces this three major species under stoichiometric condition. You have CO2, alpha moles, beta by 2 moles of H2O, and then N2. N2, these many moles of N2. Okay, we are assuming that the temperatures are less, nitrogen is not oxidized. Okay, so now the rate of progress of this reaction or the reaction rate Q dot R is given by Q dot R is equal to, you know, the same whatever formula we discussed earlier for elementary reaction. Whatever we have discussed here for elementary reaction, same formula we are using here. This term is Arrhenius rate constant K term. K is A naught exponential minus EA by R bar T multiplied by fuel concentration raised to the power small a, oxygen concentration raised to the power B. Here I have ignored nitrogen because it's oxygen that is what is contributing to this exothermic combustion reaction. So I ignored N2, consider only O2 here from combustion perspective. So the rate of progress of this chemical reaction, single step reaction, is proportional to fuel concentration raised to the power A, oxygen concentration raised to the power B, multiplied by some constant K. And this constant is important because it captures two important effects. One is A naught, that is frequency of collision. Other one is EA, where the energy, activation energy is provided to form radical during the collision. Okay, so it captures these two important parameters. That is the physical meaning of this term K. So this is how a reaction rate will progress. Now this EA, A naught, small a and small b have to be determined through experiments. So as I said, shock tube is one of the equipment that is used, or you can use something called flow reactors. These are the equipments that are used to get the rate of progress. Experimental measurement of rate of progress of a chemical reaction is done with shock tube or flow reactor. By using these experiments, you will be able to get the rate of progress Q dot R. From this, you will be able to get A naught, EA, small a and small b, which are provided to you in the form of table. If you could look at the table that I have sent to you over email, the values of A naught, EA, small a and small b are provided for important hydrocarbon. It's a hydrocarbon air combustion, and for that you have these values. And these values, as I said, comes from this equipment. Okay, based on experimental measurement, these constants are arrived at for important hydrocarbon. That can be used to solve problem involving global single step reaction. So now I have the reaction rate progress. Now with this, I'll be able to find the consumption rate of fuel, which is one of the reactant, consumption rate of oxygen, which is another reactant. This is what is the transient information that we are interested in. We want to find the rate of consumption of reactant. which include fuel and oxygen. So you can express rate of consumption of fuel as d upon dt fuel concentration, which is rate of consumption of fuel, which is equal to minus q dot r. What is this q dot r? Q dot r is the reaction rate as we have discussed now, and this is multiplied by 1. It's 1 multiplied by q dot r because in the stoichiometric hydrocarbon combustion, you have 1 mole of C alpha H beta undergoing this reaction. What does this negative sign indicate here? The negative sign indicates here that there is a consumption of fuel. So this just indicates that there is a consumption of fuel. That's why you have introduced the negative sign here. Similarly, rate of consumption of oxygen is given by d upon dt, oxygen concentration, that is equal to minus, it's a consumption, so negative sign is there. Q dot r multiplied by alpha plus beta by 4, because you have alpha plus beta by 4 moles of oxygen available in the stoichiometric equation. Okay, reaction rate progress multiplied by the coefficient, right, will give you rate of consumption of oxygen. Similarly, so these are reactants. These are reactants, and I have find out the rate of consumption of reactant. Next, I can find out similarly the rate of formation of products. So I have 3 products here, and out of which CO2 is one of the objectionable pollutant. I can find the rate of production of CO2 or rate of formation of CO2. Right, d upon dt CO2 is equal to alpha times q dot r. What is this alpha? You have in the combustion equation alpha moles of CO2. So alpha multiplied by rate of progress will give you rate of formation of CO2. This is positive sign because CO2 is formed. It's on the product side. Fuel and oxygen are on the reactant side. They are consumed during a chemical reaction, combustion reaction. Similarly, rate of production of H2O, which is other major species, rate of formation of H2O is given by d upon dt H2O, that is equal to beta by 2 q dot r. This is reaction rate progress, that is multiplied by beta by 2. What is this? Beta by 2 moles of H2O I have in the overall global reaction. So I am multiplying q dot r with beta by 2 to get the rate of production of H2O. Okay, so from the rate of consumption of fuel, I'll be able to find the rate of heat release. This is again another transient information you need to find. Heating value, whatever we discussed earlier, is only a gross value. It's a property of the fuel. Okay, that doesn't give you any information about time-based thermal energy release. Time-based thermal energy release is given by kinetics. Okay, from the single step formulation, you will be able to get this heat release rate. That is equal to d by dt fuel with a negative sign. Why I have introduced negative sign here?
Consumption.
Yeah, it's consumption, and already you know that d upon dt fuel is nothing but minus q dot r. I have again introduced another negative sign here because I want heat release rate to be positive. That is the reason, minus of d upon dt fuel. So this is nothing but minus q dot r. M with a subscript fuel. This is molecular weight of fuel. Okay, this is molecular weight of fuel. You are multiplying this with molecular weight of fuel and QZ. And QZ is nothing but heating value. Okay, so this is in kilo or megajoule or kilojoule per kilogram. This one is kg by kilomole or gram by mole, and this one will be concentration will be kilomole by meter cube. I am writing in standard SI unit. Time is in second. So this kilomole will vanish, kg will vanish. You will get megajoule per meter cube second. That is the rate at which the thermal energy is released by burning unit volume of fuel. Okay, so heat release rate can be calculated based on the consumption rate of fuel with a simple single step global reaction. This is one of the important information, as you know, in IC engine context, because thermal energy release provides an estimate of the energy that is available for conversion to work. Okay, IC engine is a energy conversion device. We need to know the thermal energy release or the energy that is available for conversion to work, and that is provided by this term HRR, which is heat release rate. Okay, the rate at which the thermal energy is released is given by this equation. From this, you will have an estimate of how much of work that can be produced per unit time, which is nothing but power output in the IC engine. So with this, the second chapter is over, concepts are over. Now, as I said, we are going to discuss the assignment problem. There are 5 problems. Okay, what I will do, I will go through the solution procedure for this 5 problem. Just take a note of it. Mail. I will evaluate and send it to you. So we have 2 assignments for this course. This is one of the assignment. Clear? Any questions?
Sir, only one thing I want to ask is that rate of consumption of fuel is minus QR, and you have told that we have multiplied by 1, coefficient 1. So, I could not gather that point, sir. I'm sorry.
So here, this consumption rate of fuel, d upon dt fuel, is written as minus q dot r. You are asking about 1, right?
Right, sir.
That 1 comes from the reaction, global single step reaction you have considered here. That 1 comes from here in this equation, chemical equation.
Okay.
So this equation has 1 mole of C alpha H beta plus alpha plus beta by 4 moles of air, which is O2 plus 3.76 N2, alpha moles of CO2, beta by 2 moles of H2O, and then alpha plus beta by 4 into 3.76 moles of N2.
Okay, sir. So if I multiply this whole equation by 2, that this will become 2, right, sir?
Yes. So what I am first finding out from this reaction, chemical reaction, is Q dot R. Q dot R provides me the rate at which the reaction proceeds. Okay. Now, if I want to find the consumption rate of reactant or formation rate of products, I will multiply this Q dot R with the corresponding coefficient. For fuel, the coefficient is 1. For air, the coefficient is alpha plus beta by 4. For CO2, the coefficient is alpha. Did you get what I am saying?
Got it, sir. Got it, sir.
Okay, so this all this comes from this chemical reaction you have considered. Basically, Q dot R is assigned to this particular chemical reaction. I'm finding out the rate at which the reaction, this particular reaction, progresses. From this, I am finding out what is the consumption rate of fuel, consumption formation rate of products.
Noted, sir. Thank you so much.
Okay.
Sir, I wanted to ask regarding this is regarding the NOx emissions, not on the topics that you have covered, sir.
Okay.
For 2-stroke engines and 4-stroke engines and ships which we use, we have fuel oil, heavy fuel oil, and diesel oil, and marine gas oil in use, sir.
Okay.
So for reducing the NOx levels, basically we apply Miller cycle there. So the inlet valve closure is either advanced or retarded. So in our engines, normally we have the inlet valve closing a bit earlier, sir. So what happens? It helps to the air to expand more, whereby the temperature reduces, and hence the exhaust gas temperature also reduces. Thereby the NOx emissions are much reduced. But during our sessions, you were mentioning that the NOx emissions will happen more than 2000 Kelvin. If I'm not wrong, sir. But why? But there, in our exhaust gas temperatures, we get normally around on the range of 300, maximum up to 500, sir. So after turbocharger, it will be close to some 400 to 450 degrees. So, so why there NOx emissions are happening rather here? It is not. Is it because of this?
Your question is well taken. I think you should not get confused with the exhaust gas temperature and in-cylinder temperature. So when I say NOx forms at 2000 K and above, it is in-cylinder gas temperature during the combustion event.
Okay, sir.
And what you are talking is the exhaust
gas temperature. Correct, sir.
Exhaust temperature is after the combustion event, after you extract whatever thermal energy left out. In fact, if you use Miller cycle, you are in fact utilizing the exhaust thermal energy more effectively because you call it as an extended expansion process, right?
Correct, sir. Exactly. Sir.
Extended expansion, because your thermal energy otherwise is wasted. When you let out exhaust gas into surrounding ambient, you are not recovering that into work. It is simply let out into atmosphere. Almost some 30% of thermal energy is wasted. That is why you use a turbocharger or extended expansion using a Miller cycle to recover that thermal energy.
Correct, sir.
Okay,
We
that
have
temperature,
recirculation.
whatever you are measuring is at the exhaust level, which is going
Yes,
to be anyway wasted. Whatever
Okay.
temperature I highlighted is in cylinder temperature.
Clear, sir. Clear, sir. Understood, sir.
Okay.
Understood,
Thank
sir. Clear. Thank you, sir. Thank you.
Yeah, thank you. Okay, so let us get back to this five problem. Note down the procedure, solution procedure. I will read out the problem and I will discuss briefly the procedure for solving the problem. Note down and solve the problem by yourself and send it to me as an assignment. Is it clear?
Yes, sir.
Okay.
Definitely.
Yes, sir. Yes, sir.
Clear.
Yeah, so what I will do, I will first read this problem one. The problem one involves estimate the lower heating value of gasoline and diesel whose higher heating value is 46.53 and 45.76 megajoule per kilogram respectively. Take the molecular formula of gasoline and diesel as C8H14 and C14H25 respectively. Latent heat of vaporization of water is 2.44 megajoule per kilogram at 298 Kelvin. Also estimate the stoichiometric heat of combustion in megajoule per kg of air. Okay, megajoule per kg of air. Actually, this problem involves estimating lower heating value of gasoline and diesel. What is given in the problem is higher heating value of gasoline and diesel. So you have higher heating value, which can be measured. We discuss about this, which can be measured by using equipment like bomb calorimeter. So whatever you measure using that equipment is higher heating value. What you need to calculate thermal efficiency or first law efficiency of IC engine is lower heating value, because you never recover latent heat of H2O in IC engine system. In IC engine system, combustion system, H2O leaves the engine system at a higher temperature. Okay, so you are not going to condense H2O into liquid. Once you condense H2O vapor from vapor phase to liquid phase, you will be able to get the latent heat, and that will be added. That heating value is higher value, which is what you measure. But since we cannot recover that latent heat in IC engine system, and the H2O leaves as a vapor phase, not liquid phase, you have to use only lower heating value when you calculate thermal efficiency. So there is a formula we discussed. So this problem involves application of that formula, whatever we have discussed, to get lower heating value from the given value of higher heating value. Okay, so for both gasoline and diesel, this higher heating value is given. So higher heating value of gasoline and diesel is given, and you need to know the molecular formula of gasoline and diesel, otherwise you cannot proceed. So here some approximation is made. Gasoline is approximated as C8H14, diesel is approximated as C14H25. Okay, these are the molecular formula for gasoline and diesel, and the values of higher heating value for these two fuels are given. Latent heat of vaporization of H2O is given. So these are the information that are available with you, and with this you are asked to find lower heating value of gasoline and diesel. So you know how to connect lower heating value with higher heating value. We already discussed about that. So this is the equation I have written for gasoline. Similarly, you can write it for diesel. Higher heating value is equal to lower heating value plus the heat that you recover by condensing H2O to liquid phase. That is nothing but mass of H2O given by number of moles of H2O multiplied by molecular weight of H2O, which is nothing but mass. So please remember that this is from the fundamental equation. Number of mole is equal to mass by molecular mass, or molar mass, or molecular weight. N is equal to M divided by small m divided by capital M. Okay, this is mass of H2O multiplied by latent heat of vaporization of H2O, and you are dividing that with NF AMF. What is this NF into MF? We already discussed about this. This is mass of fuel, right? Because heating value you always express in terms of megajoule or kilojoule per kg of fuel that is burnt. The numerator you will have megajoule. The denominator we have kg of fuel, so that you can add this. Okay, unit should be consistent. You have to pay attention to the unit. So this is the equation we already discussed. So only information you need to know to get lower heating value. This is what is asked in the problem. This is given in the problem. Okay, and this is also given in the problem. Now you need to know the number of moles of H2O. How do you find this?
Using a stoichiometric equation.
So you have to write the stoichiometric combustion equation for this two fuel, gasoline and diesel, to get the number of moles of H2O. Okay, and molecular formula is given. From the formula, you can write the stoichiometric combustion equation for gasoline and diesel. From that, find out number of moles of H2O. Once you get it, you are done. You will be able to get the lower heating value. The second information asked in the problem is stoichiometric heat of combustion in megajoule per kilogram of air. So here we are talking about the thermal energy in megajoule per kg of air, not per kg of fuel. So what is the significance of this term, stoichiometric heat of combustion? You know, you design an engine with a given capacity defined by displacement volume. Now my question to you is the displacement volume defined based on air mass or fuel mass?
Air mass, sir.
Air mass. So always fix the engine capacity based on air mass. Is there any specific reason?
Because air is in high quantity, sir. Because
yes, fuel quantity is negligible compared to air quantity. So whenever you design an engine, the important parameter is the capacity or displacement volume. And that displacement volume is specified in terms of how many kg of air that you can fill in the engine. Once you know the kg of air that you can fill in the engine, you know how much fuel you can burn, because fuel mass and air mass are interrelated. For a given air mass, there is a well-defined fuel mass, because that is defined by phi, equivalence ratio. You can burn fuel and air only if they are combined in a particular proportion. So from the air mass, you will be able to fix fuel mass. Okay. Once you know that, you will be able to get how much of thermal energy is released, and that will give you an estimate about how much of power that the engine can produce. Engine can also be visualized as an air pump. Depending on how much air you can pump in, you can add fuel mass accordingly, and you can get the power output accordingly. This is where the turbocharger or supercharger plays a important role in increasing power output. You know, with supercharger or turbocharger, you can fill in more air mass, right? By filling in more air mass, you are actually increasing the power output of the engine with a given capacity. That is what you do with supercharging or turbocharging. So this is one of the important terms, stoichiometric heat of combustion, from an engine design perspective, because this parameter, stoichiometric heat of combustion, is defined in terms of megajoule of thermal energy release per kg of air. Based on how much air you can fill in, okay, you will get an estimate of the thermal energy that is available in megajoule. Okay, from this thermal energy available thermal energy, you will get an estimate of power that can be generated with the given engine capacity. So you can say that this provides me an estimate of thermal energy that is released with a given engine capacity that will help you to reach what will be the power output of the engine with a given capacity. Basically, it is relating power output and capacity of the engine, this parameter, stoichiometric heat of combustion. Okay, this is the physical meaning of this parameter, but the question is, how do I calculate? Can you tell me, how do I calculate stoichiometric heat of combustion? I want megajoule per kg of air. And whatever you need to get megajoule per kg of air is available in the problem. All the information are available in the problem. Only thing, you have to write an equation for stoichiometric heat of combustion.
Terima. You know the stoichiometric equation?
How will you get this? You can give a try.
Sir, just based on the units, I'm just saying that there has to be a ratio at the denominator, which is
kg of air.
Yeah.
Sir, based on the air fuel ratio, means stoichiometric ratio, we will have to reverse calculate the number of moles and then.
Okay, so already you have heating value. Okay, which heating value you will choose? Lower heating value, because it's somewhat realistic, more realistic than higher heating value. And this lower heating value is expressed in megajoule per kg of fuel. Okay, kg of fuel that is burned. But what I want is megajoule per kg of air that is burned. Okay, so how do I convert this?
Sir, basically I have lambda, such a metric. So you have taught us the formula like mass of fuel divided by mass of air, actual versus stoichiometric.
Yeah.
And by using that formula, I can get what is the value of what is the mass of air that will be there in the system. So if
you are asked to find stoichiometric heat of combustion, you are defining this term under stoichiometric condition. No need to go to phi here.
So that means I will multiply the like mass of like whatever value I have got, sir. 14 point.
Can I say that I can use this?
Yes.
So this is known to you for gasoline or diesel. Stoichiometric air to fuel mass is known to you for gasoline and diesel. Once you write the stoichiometric combustion equation, you will be able to get this term. Mass of air by mass of fuel under stoichiometric conditions. Okay, so this LHP is nothing but megajoule per kg of fuel. And what you have in the denominator, mass of air by mass of fuel. So this will be kg of air divided by kg of fuel. So fuel, kg of fuel will vanish. What you finally get, megajoule per kg of air. And this is under stoichiometric conditions. Okay, so once you have this LHP, once you have mass of air by mass of fuel by stoichiometric conditions, you will be able to get this stoichiometric heat of combustion. Can you please mute your mic? Okay, so this is what you have to do. Stoichiometric heat of combustion for gasoline is given by this equation. Similarly, you can write it for diesel. Second problem. Gasoline is approximated to have a chemical composition of C8H14. Determine the exhaust product composition for gasoline engine operating with a fuel air equivalence ratio of 0.83 with the assumption of complete combustion. Part B, you have to find percent XSR. Percent XSR. So here you have to find the product composition. You are asked to find the product composition assuming complete combustion. Is this assumption valid? Complete combustion assumption, is it valid with a given phi value? When phi is 0.83, what is the condition? Combustion condition?
It's rich, sir, actually.
Is it rich?
It will be lean, sir. Lean, sir. Lean, sir.
P less than 1 is lean, P greater than 1 is rich, right?
Yeah, I'm sorry, sir. I'm sorry. Yeah.
So this is lean combustion. Lean, when you say that it is lean, it means you have more oxygen. When you have more oxygen, you can assume that it's complete. It's a reasonably good assumption. So you have complete combustion because you have more oxygen. P is only 0.83, less than 1. This is the condition. You have to write the equation, combustion equation with gasoline air, right? Under these condition, lean condition. With that, you have to find the product composition. Okay, so what is product composition here? What are the products you can expect under these conditions?
CO2, H2O,
only major
and H2O.
So this
only
is
four product will be there.
4 species. So this is lean combustion. The products will be
CO2, H2O, N2, and O2.
CO2, H2O, N2, and
O2.
O2. So you have only 4 species in the product. CO2, H2O, N2, and O2. You are asked to find the product composition, exhaust product composition. So when you calculate product composition, I would recommend you not to find in moles. Mole is absolute value. You write chemical equation in molar basis, right? So don't get the values in mole. Rather, you get product composition in mole fraction. So mole fraction of any species, Ni is given, Xi is given by Ni by Nt. So this is total number of moles of product, all the product, and this is number of mole of species I. This is what is mole fraction. This is mole fraction. Whenever you are asked to find the product composition, you find the values in mole fraction because this is normalized value. You should not use absolute value for any comparison. when I say normalize, I mean to say that you are dividing this number of moles, which is an absolute value, by total mole. Then you are normalizing it, right? So mole fraction is a normalized value. Mole is absolute value. So here you are asked to find product composition, get the product composition in mole fraction. So you write the combustion equation with phi equal to 0.83. Molecular formula of gasoline is given to you. Again, this is an approximation. This is a multi-component fuel. We consider only C8H14, right? Based on some approximation, we arrived at the number of carbon atom and hydrogen atom for gasoline. So this is an approximation. With this formula, you have to write the combustion equation with phi is equal to 0.83. Find the number of moles of these four species, get the mole fraction. That is what is asked in the first part, exhaust product composition. The second part, you are asked to find the percent excess air. What is percent excess air? How do you define? Percent excess air is defined as actual air mass minus stoichiometric air mass. So this is air mass, actual air mass minus stoichiometric air mass divided by stoichiometric air mass. So I'll write it here. Mass of air under actual conditions minus mass of air under stoichiometric condition divided by mass of air under stoichiometric condition. This is asked in percentage, so you are multiplying it by 100. So this is percent excess air. Okay, to get this percent excess air, what is the only information available to you? Phi. Only information available to you is phi. So I would like you to carefully modify this equation in terms of phi. In terms of phi, you can write this equation. Once you write this equation in terms of phi, you will be able to get the percentage excess air, which is what is asked in the problem, the second part of the problem. Okay, first part you are asked to find product composition, second part percentage excess air. Okay, so you can get it by writing the combustion equation with phi equal to 0.83. It's time up. I stop here. I will continue this in the next class. If you have any questions, you can ask me.
Yes, sir. I was just going through notes. One thing I want to ask you is that regarding application of equation of equilibrium, there were 6 unknowns actually in the system when we. So because of dissociation, there was a H2O dissociation and CO2 dissociation, and because of that, CO and OH was the 2 additional, what I mean to say, radicals that were formed, and the total unknown was 4 plus 2, 6. Whereas by using equilibrium equation, we could find only one additional.
No, I have demonstrated with only one additional chemical equilibrium based equation. I think the equation I have written for that is lean combustion. If at all it is a rich combustion with the dissociation, we will have more species.
So basically, sir, that means if there is 6 unknown, we have to have 6 equation actually in that. Right?
6 equation. You can write 2 equations based on chemical equilibrium, 4 equations based on atom balance. If you have to write 2 equations based on chemical equilibrium, you have to consider 2 chemical reactions. The example I have shown you is only one.
It was only 5. Okay, I got it, sir.
So I have written water gas shift reaction, chemical reaction. From that I arrived at Kp value. Right? If you have 6 unknown, you write 2 chemical reactions. Right? Write 2 equations for Kp based on equilibrium, chemical equilibrium. Then you have 4 plus 2.
Thank you, sir. Thank you so much.
Okay.
Noted.
Sir, one doubt, sir.
Yes.
This is based on my the testing experience. Just I wanted to clarify.
Okay.
So when we have done the trials with the engine, so whenever the fuel temperature goes up, the power is getting reduced. But when you have explained in the class system, you more the temperature, it will be the faster the reactions.
Yes, chemical reaction.
So, but when I'm going with the higher temperature in the fuel, my power is reducing by almost some percentages with respect to less fuel temperature.
So generally we will run the engine under ambient fuel temperature condition. When you talk about higher fuel temperature, how did you achieve that higher fuel temperature?
Because it's when I'm using in the vehicle itself, so it will be a circulated fuel. So it will come back to tank. The return fuel come back to tank. So it just keeps on doing it. So I'll get the higher temperatures.
So you mean to say that the return fuel is at a higher temperature, and that is again sent back to the engine at that higher temperature,
Right.
but I am getting loss of power.
Yes.
So this higher temperature in the fuel temperature from the return line cannot be too high. It is an indirect indication that the friction wear rate in the engine is high. Basically, the power loss is due to high wear and also due to high heat loss. Okay, so because thermal energy that is released during combustion should be converted to useful work in IC engine. If there is more heat loss, then you are not recovering that energy into work. You are right. When the temperature is high, the chemical reaction will proceed at a higher rate. But whether you are utilizing that chemical energy effectively in the engine or not is a question. Based on what you are saying, I could observe that maybe the friction and heat loss are higher in your engine. That is what is causing a higher fuel temperature in the return line, right? And that is what you are observing as a power loss.
Okay. Okay.
This is an indirect inference, but to answer your question, when the initial temperatures are high, chemical reaction definitely will proceed at a higher rate. But what is happening? You are not recovering that thermal energy into useful work. Rather, it is lost. The loss is more.
Correct. Approximately, I'm getting around some 8 to 10% power loss.
So I would like you to check the wear and tear of the component, check the lubricating system, and also check the coolant system, whether they are effectively functioning.
Right. Okay. Okay.
So can it be the reduction in density, sir, of the fuel? Like, because you have told that
No, density variation with temperature is minimal generally because fuel is incompressible, right? So unlike gas, for gases the density variation with temperature is so high, but for liquids the variation in density with temperature is less. Viscosity will vary more. In fact, the higher temperature, the other reason will be at a higher fuel temperature, the viscosity will drop. Please note that when the fuel viscosity drop, you will also have a problem in the pump in terms of leakage. You can expect higher leakage. That may also cause one of the cause.
Okay. Okay.
It affects density more. Temperature affects viscosity more than density for liquids.
Yeah, sir, as you said, the drop in viscosity will cause higher wear of plunger barrels also, no, sir, for the fuel pumps.
Yes, because the lubricity properties will be affected because fuel has to function as a lubricant, as I said in the first chapter. That is one effect. The second effect of viscosity, drop in viscosity, is high leakage losses because in a high pressure system, when the fuel loses its required viscosity, the seals won't be effective. Okay, so there will be more leakage. Viscous fuel will be prone to less leakage, but less viscous fuel is prone to more leakage because of thinner nature.
Because it becomes more lighter, sir.
Yeah. What is it?
Because it becomes more lighter. That's the reason.
Lighter, yeah, thinner. That's what I use the word.
Okay, sir.
Thick fluid will have less leakage. Thinner fluid will leak more in a high pressure system.
Okay, sir.
Sir, one more thing, sir.
Yeah.
Sir, as you have told, in the fuel line, the temperature is going high. In that situation, the T10, the fuels at like they said, hydrocarbons, create a vapor lock or what, sir?
Yeah, you are right. That is again another problem with respect to fuel characteristic. When the fuel temperature is high, you can expect some vapor formation in the fuel line. Vapor lock may obstruct the flow, and also evaporative losses will be more if the system is not perfectly sealed. Evaporative losses is also dependent on T10 temperature, as I said in the first chapter.
Will there be any bleeding valve given, sir, to in case if there is any lock?
Generally, what we do is to avoid evaporative loss from the crankcase blow by, you will connect it to the intake system so that the vapor, whatever you get in the crankcase side, will be again sent back to the intake side so that you are not losing much. You are not losing fuel vapor.
Okay.
But that is a requirement of BS6 norm also in that, if I'm not wrong.
Okay.
Sir, regarding problem 2, sir, when P is 0.83, can we directly say that we have excess error of 70%? Can't we say like that?
Yeah, you arrive at with some equation. As I have given the definition for XSR, from that you can express that equation in terms of phi. Once you have that, you are done. You will be able to get the percent XSR.
Okay.
Whatever way you want, you can proceed and get the percentage, but it should be through that fundamental definition.
Okay. Thank you.
Fine. So I'll stop here. I will see you again tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you so much, sir. Thank you so much.
Thank you.